this subgroup of the etale fundamental group, then the representation rho endows the trivial bundle OY to the n, which admits an action of GLNK, and therefore through the representation admits an action of the Galois group with descent data giving a stratified bundle E on X such that pi upper star E is isomorphic to OY to the n equivariantly. Equivalently for the Galois group of Y over X. And this is what you mean by saying something corresponds to descent data. It's possible to write down a vector bundle on X whose pullback is canonically identified with trivial bundle such that the tautological action of the Galois group here becomes the action of rho there. This is the same as the construction you would use over complex numbers working with the universal covering spacer. But here we have only finite covers because we're in algebra. So such things certainly exist provided the etale fundamental group is non-zero. Yeah? Sorry? No, of course not. The rank would have gone up. It's the other way, it's descent. It's the invariant. If you take pi lower star OY and look at the invariant subsheet for G, that would be, I believe, the same. Okay, so this is correct. So such E are called for my purposes finite vector bundles, and I'm thinking of them as stratified vector bundles. Here it's pretty clear what the action of differential operators is. What about this Frobenius structure which I asserted is an equivalent thing? Here that's also easy to see. You do it like this. Suppose your representation rho is conjugate to a representation of this kind. Because after all, rho has finite image. So any subgroup of finite subgroup of GLNK is conjugate to a subgroup inside GLN FQ for some Q. So I can as well think of my rho as, or Fp to the R, let me say. Up to conjugacy, my representation takes values in some finite field, and then if you take this particular R, it's easy to see that F to the R upper star E must be isomorphic to E. Because, so to speak, the transition matrices are invariant under this particular power of Frobenius, everything will be invariant. So, such a thing, of course, therefore is F divided in some natural fashion. In fact, after dividing R times, I get back the same E again, and it repeats. So, it's a kind of periodic division. So, there's only a finite amount of data as opposed to the general case where we have infinite amount of data, but that's why, that's another way in which the bundle is finite. Now, there's a nice result of Langer and Stuhler that if, let's say, X is projective smooth over, let me say, K algebraically closed or characteristic P, these are stronger hypotheses than are really required, but for my talk, this is fine. And E locally free on X such that F to the R upper star E is isomorphic to E for some R. Non-trivially. Then E is a finite vector bundle. So in fact, these bundles which come from representations, continuous representation of the etale fundamental group are exactly the ones which have the property that some Frobenius pullback of the bundle is equal to the, is isomorphic to the bundle again. So this is a nice class of things, and it's some relationship with the fundamental group. So of course, it immediately implies that if all stratified bundles on a variety, projective smooth variety are trivial, then the fundamental group is zero. because in particular there are no finite bundles either. So it's natural to ask, some of the intuition is that these are something like torsion points in the Jacobian. That is the sort of intuition you have. And in other ways also, even in characteristic 0, these types of things with finite monodromy are somehow special. You might, the question of Gieseker is the converse true? If the fundamental group is 0, that is, there are no finite bundles, stratified bundles, are there any non-trivial stratified bundles at all? So this was proved by, so Gieseker, if pi 1 at x equals 0 are all stratified bundles trivial.
Is there an easy answer for equal to 1, the rank 1?
For rank 1, you can give a complete description of the group of stratified line bundles. It's an extension of the Picard, essentially the big tau prime to the characteristic may by the p-adic date module of the Picard variety. There's even a formula you can write down. So in particular, questions like that can be answered. Because it's easy to see, we have a very good control on line bundles. So if I say a stratified vector bundle is a sequence of bundles, here it will be a sequence of line bundles, so basically it will be a sequence of points in a Picard variety and must be compatible multiplication by p, and it's a matter of writing everything down easily. Not so difficult. So theorem, this question was posed, or I don't know if it was a conjecture, in the 70s. So this was an open problem for a long time and was solved finally by Ellen and Vikram Mehta. The paper appeared in 2010. Yes, if pi 1 at x equals 0 for smooth projective x, over k equals k bar of characteristic p, then all stratified bundles are trivial, on X are trivial. So now what I wanted to talk about today was some work I've done with Ellen where we tried to look at generalizations of this type of question. There are various ways in which you can generalize it. One of them is the following result, the following statement which we managed to prove. Let me write down our theorem. Let f y to x be a morphism of smooth projective varieties over an algebraically closed field of characteristic P. Suppose the homomorphism f lower star on etale fundamental groups is 0, then the pullback to y of any stratified bundle on X is trivial, has a stratification. This is one relativization. There are others. you could think of. For example, suppose it's an isomorphism. Is there an equivalence? I believe Parameshwaran is working on it along with somebody else. So I don't know what progress they made. He might be able to tell you. And there are probably other things we can do. And then you can ask, for another line of investigation is, what if you drop the properness hypothesis? To what extent? And with En all mu stable. I study these first. And then to study extensions. There will be 2 steps in each of the arguments. So let's first look at let me look at step 2 in the case of Esnault method. So this is step 1, and step 2. Suppose you've already done step 1 in their problem. Then you've argued that any irreducible En must be the trivial line bundle. The only stratified irreducible object is the trivial bundle of rank 1. That's what you have to prove in step 1 in their problem. Granting that, I claim step 2 is pretty easy, because basically you'll have to study things of this form. Suppose I tell you a general E has a Jordan-Holder filtration where the quotients are irreducible, and I also told you each irreducible is OX as a stratified bundle. The general E has a filtration where each quotient is OX. So I took a 2-step filtration. If I can show that split, then by induction I can split a more general Jordan-Holder and be done. So I'll have to just study such things. In the category of stratified bundle is an irreducible object. There are no non-trivial sub. No. At least it's not obvious. Well, I suppose it probably does follow. Yes, it does follow. It seems reasonable. Yeah, indeed it follows. Yeah, mu stability does guarantee, absolutely. But more to the point, irreducibility guarantees mu stability. Deep enough. That is sort of the non-obvious, the direction where you have to argue, which indeed, yeah. There are no non-trivial mu stability says there are no non-trivial subbundle at all with mu equals 0, let alone stratified subbundles. So anyway, let's look at such an extension. Then, of course, when I write this, I mean as stratifications, but then there's an underlying E, which is the E0 of my stratified thing. So this E gave me a point in X1 of OX, which is just H1 X OX. So to speak, inside this, I have X1 strat OX. So it's natural to think of whatever this is something sitting inside H1 X OX, and I can tell you what it is. In general, for any smooth projective X, the stratified extensions of O by O are going to be given by H1 etale X Z mod PZ, tensor Z mod PZ K sitting inside this. So how does one think of this sitting inside this? This comes from Artin-Schreier theory. So in Artin-Schreier theory, basically you try to understand the action of the Frobenius on H1 X OX.
So suddenly you're looking at rank 2 bundles.
Let me first make a statement about rank 2 bundles. Then if I took a general rank, if I know, for example, the last 2 things give me an extension of O by O, that extension is split. Then you can imagine how you can propagate that up the chain. So by working by induction on the length of a chain, I can argue, in fact, there are no non-trivial extensions at all. Or you can do other homological algebra. If the category of things or something has some X1 vanishing, automatically higher Yoneda X must vanish because of the cup products. There must be some abstract category statement too. Which, yeah. We'll discuss that later. Those technical questions about things we'll talk later. Let me just give a quick indication of what's happening here. You have the Frobenius map. This is not this is an abelian group homomorphism, but it's not linear over the ground field. It's p-linear. f upper star of alpha times x is alpha to the p f upper star x for a class x and a scalar alpha. So if you have any finite dimensional vector space V, so I need a comment about such things. Let me just do that here. Let me say phi. If I have a P linear map, it's always possible to decompose V as Vs directs from Vn canonically, where phi restricted to Vs is bijective and phi restricted to Vn is nilpotent. And in fact, phi restricted to Vs is just take the fixed points under phi on V, tensor, this is an FP vector space. Sorry. Vs has this description always. You just take the fixed points under phi. Of course, it's a fixed point, it's in the semi-simple part, certainly not in the nilpotent part. Take the k span of those things, that is exactly the semi-simple part. So to speak, the theory of eigenvalues here says that you break the space up into the nilpotent and semi-simple, and in the semi-simple I can find a basis of fixed vectors. That's P-linear algebra. So I'm applying that theory to this and telling you in particular what does it mean to study this. That's Art and Schreier theory. On H1, X, O, X, the phi fixed vectors are naturally identified with the etale cohomology with Z mod P coefficients by Art and Schreier theory. Okay, so that's standard characteristic P algebraic geometry. So of course, in the context of NO meta, obviously if the variety is etale fundamental group 0, its etale cohomology H1 with Z mod P coefficient is also 0. This space is 0, there are no extensions, etc. This is the argument which doesn't make sense in my problem, the work with NO. Our theorem will be, our version of step 1 will be that if you take an irreducible stratified bundle, one of these good ones with stable underlying vector bundles, and pull it back, the pullback is trivial. There's nothing says it's a rank 1 or it's the trivial bundle or anything like that. Originally it's a complicated bundle. So when I have to deal with extensions, I can't just stick to this easy case and throw out the problem. I have to do something new. This is really where you have to do something new. Anyway, step 1, let me say a little bit. It kind of works the same way for both the problems. Suppose you have an E irreducible. So now we're looking at step 1 for both problems combined, so to speak. So look at E, which is En sigma n, and En stable of rank, let's say R. And in the NO meta context, I'll have to conclude R equals 1 and the underlying bundle is trivial. That's what I want to conclude. In my case, I just have it, whatever it is. So I'll look at MR moduli of stable. And let me just say now, the rest of the argument, I'm going to assume the ground field is algebraic closure of finite field. Because I want to use Khrushchevsky. In general also you can do specialization, it gets more nasty and complicated. I mean, it's not, an expert in the theory of vector bundles will say, all right, if this is what works for FP bar, how would I make the argument work with specialization? After some thought, you are able to manage it. But it gets messy, but there's nothing really interesting. I think
Stable means Gieseker stable.
mu stable. There's an open set inside the other one. I'm not, it's just a projective. And in fact, stable vector bundle. I'm not bothered about sheaves. Anything coming from a stratification will lie in this open set of rank R. inside I have various sets. Let Si be the following set. Yes. One second. So let's look at stratifications of a fixed rank. Look at all of them. For each of them, choose an index I greater than or equal to 0 and look at the ith bundle appearing in that stratification. That gives me a set Si. It's a set of closed points. This sequence of these sets have this structure. That's because if I have anything E, I have in ZR1 cross ZRS such that there exists E, a vector bundle, there exists E contained in E, F1E contained in F2E, a filtered vector bundle on X such that Fi mod Fi plus 1E is isomorphic to this Ei, the ith term in my tuple, the ith coordinate, and little f upper star E is not F nilpotent on Y. This is a rather tricky looking definition. The whole point is to write down this definition. Then somehow study its properties, everything comes out. Okay, so what is this set? It's a kind of bad set of some sort. Suppose I'm not in the bad set. Suppose I have my stratification and I prove that the tuple corresponding to a stratified E, so E also gives me a point X in ZR1 cross ZRS, right? Where this corresponds to sort of E 0 I mod E 0 I plus 1, so to speak. Yeah? Yeah, couple of minutes. I started a little late because of the business with the mic, so I have 5 minutes. Sorry about that. So what I want to say is I'm not in the set A, then every possible multi-extension is F nilpotent after pullback. So the particular multi-extension which underlies my stratification is also F nilpotent. But then a fixed power of it is trivialized. A fixed Frobenius power becomes trivialized. But anything stratified is always a fixed Frobenius power of something else which is stratified. So I would conclude that the bundle is trivial. So the point is to prove that if you have a stratified bundle, the points don't lie in the bad set. So instead of that, what you prove using Grushovsky, let me not give the details, you remember you have a U contained Z equals ZR1 cross ZRS such that we have the Frobenius operator which is a dominant map from Z to Z, but it's a morphism on U. And all my stratified points lie inside U. Then I can define U1 equal to U, U2 equals phi inverse U, U3 equals, phi inverse U2, and so on. In other words, UM is the set where M times I can apply the operator phi, and still it's defined. So for example, all periodic points will lie in the intersection of all UMs. So the main lemma, the key lemma, is to prove the lemma UM intersection A is the empty set for M sufficiently large. The point is to prove this assertion. Then automatically the stratified points will lie in any UM large enough, so they would not lie in A, and therefore it'd be done. This you have to prove again using Grushovsky. So what you do is assume it's not true, then each intersection is non-empty, take the Zariski closure, it's a decreasing sequence of closed sets, stabilize it. Unfortunately, the Frobenius is no longer dominant, but doesn't matter, take the image of the Frobenius, take the image of the square of Frobenius, etc. That's a further decreasing sequence. Now when you shrink all the way down, and every time things are non-empty by the hypothesis, you would have constructed somewhere some closed set where the Frobenius becomes dominant. Then you would have torsion points, that is finite vector bundles. Those finite vector bundles continue to lie in A, because I'm only looking at the closure of the intersection with A. And I want to contradict the fact that it's non-empty. So everything is non-empty. Therefore, I would get a finite vector bundle which lies in the intersection. But according to this other lemma, this lemma here, any finite vector bundle does have the property that the corresponding tuple doesn't meet A. Because for any finite vector bundle, an arbitrary multi-extension has the property that it's some Frobenius pullback is a finite vector bundle. But then under our home mapping, finite vector bundles pull back to trivial bundles. Because the induced map pi1y to pi1x was 0. So every finite vector bundle on X pulls back to the trivial bundle on Y. Therefore, every bundle which is sort of Frobenius upper some Frobenius power of it is finite, the Frobenius power will pull back to the trivial bundle. Therefore, the pullback bundle is F nilpotent. That's the argument. Thanks. Yeah, I think it's better. Yeah. Or during T.
Where can I get?
Where do you want?
Okay, no problem.
Belt, is it? Oh, thanks, Pramesh. Thanks. Yeah, sure.
Okay, so it's a pleasure to share the session. We keep talking about complexity of one or two. Hey, the title actually told to us not to. Oh. Characteristic of mononomic groups or cyclic hours of P.
Thank you. First of all, thanks to the organizers. It's been a very nice conference. I liked it. And I would like to say a couple of things about Nagaraj. I had heard of him before. You know, my father was in the maths department in Mysore University, but I had never met him. And I met him on the train. We were both traveling to Mumbai to accept this research scholarship from Tata Institute. That was the first time I met him. And of course, it was more than 24-hour journey, maybe more than that. So we got to talk mathematics quite a bit. And as usual, you know, my way of doing mathematics was to, or doing anything, is to speak first and think at all if afterwards. So I really learned from Nagaraj that it's a much better thing to do it the other way. Yeah, and we were really good friends in Tata Institute. I missed him when he left, and I'm going to wish him all the best in future too. Thank you. So The things I'm going to talk about were actually sort of motivated by a definition of Peter Sarnak. Actually, this definition is not due to him, but somehow it's attributed to him. So what we do is to look at finitely generated subgroups. Of integral matrix groups like this. So given this gamma, you can take the Zariski closure of gamma. So gamma is contained in the integer points of G, which is by definition G intersect SL and Z. So one says that gamma is thin if gamma has infinite index in GZ. And one says that gamma is arithmetic So the problem is that given a finitely generated group, there is no algorithm to tell you when it is thin or otherwise. There is no such algorithm. That is a theorem, that there cannot exist such an algorithm. And so you cannot decide whether a group is thin or not by just looking at it, so to speak. So Sarnak asked this question whether, if you took some very naturally occurring groups like monodromy groups, he had this idea that most of these monodromy groups should be thin groups. But in fact, it is exactly in contrast to a question by Griffiths and Schmidt, which I will explain in a minute. So the monodromy groups I'm going to talk about are actually associated to fibrations. So suppose X over S is a C infinity locally trivial fibration of manifolds. Most of the time the fibers are compact, but that's not necessary here. So I'm going to assume that if F is the fiber, I look at the homology or cohomology modulo torsion. So I don't want to think about torsion. And this is in general a finitely, that's what I'm going to assume, that this is a finitely generated group. So given such a locally trivial fibration, for every point S, I have this fiber f of S, and I can replace the fiber by the homology group, mod torsion. So this forms a local system on the base. So to every such local system is associated a representation of the fundamental group acting on this homology group. So we get a representation with some base point. It's not. So the image rho is called the monodromy group, and this is the monodromy representation. So Griffiths and Schmidt were looking at the case when such a locally trivial fibration is actually a morphism of varieties, where the fibers are smooth projective varieties. X over S morphism of varieties over C, and each Fs is a smooth projective variety. In fact, they ask if in such a case the monodromy group is always an arithmetic group in the sense that it has finite index in its integral Zariski closure. So, question Griffith-Smith. I think this question was asked in a conference in Tata Institute, Mumbai. Is the monodromy group always an arithmetic group? So I can't resist repeating my joke. By the way, this talk I have repeated at least twice before, except that there is a little bit that is new for today, I hope. The counterexamples to this question were given in 1871 by Schwartz and Picard, apparently. But what they did was interpreted by Deligne-Mostow as saying that, in fact, the monodromy is in general not an arithmetic group. So the first counterexample, in some sense, was given by Deligne-Mostow. Give counterexamples to this conjecture by looking at. So, in their examples, you have this base which parameterizes a family of cyclic covers of the projective line. By looking at families of cyclic covers of P1, where the sort of ramification data is fixed, but the ramification points are moving around. So the simplest example of this kind of thing is the family of elliptic curves. So let me just give this. So suppose my base is P1 minus 0, 1, infinity. And I have this for every point lambda here. I have this elliptic curve whose affine part is given by this equation. That's the fiber. So you can ask what the monodromy representation is. In fact, it's already given in alphas that the monodromy. So this is the plane minus 0, 1. So I could take the loop around 0 and the loop around infinity. These two loops generate the fundamental loop. So monodromy takes, with respect to some fairly natural basis, it takes the loop around infinity to this matrix. So the monodromy group is the group generated by these two matrices inside SL to Z, and of course this has finite index. It's more or less a congruence of group of level 2. Okay, so the monodromy is arithmetic. So you could ask for a similar such things when you could take double covers of P1 where instead of degree 3 you could replace it by a degree n polynomial. So the base S is to be the space of polynomials F monic with distinct roots, monic of degree n. So the fibers for every S in S, for every polynomial f, I'm going to look at the curve y square equals fx. And take its completion. So in here, it's easy to see that the fundamental group preserves the cup product on the H1 of this curve. So the monodromy representation, it preserves this intersection form, is a homomorphism from pi1 of this with some fixed base point, if not, into the symplectic group. And so there is a theorem by Acampo, very old theorem, which says that the image has finite index in sp2G. Okay, I have to say what this 2G is. It's actually related to n. If n is odd, n is 2G plus 1, then this sp2G. If n is even, then it drops a little, 2G minus 2. And what's more, the image, in fact, is more or less the congruent subgroup of level 2. There is a little bit of ambiguity about which I don't want to say anything. So far I have listed the cases where the monodromy is arithmetic. What I want to say is that in general it's not really very clear what's going on. I mean, there is no nice criterion to say, for example, if I take an arbitrary family of cyclic covers of P1, these are double covers of P1, where the monodromy is arithmetic. If I took an arbitrary family, it's not clear whether the monodromy group is arithmetic or not. So fix d greater than or equal to 2. And for the moment, I fix n distinct points. So for my base is supposed to be this set of points. So I also fix integers. Fix n integers like this. So I can look at this family y to the d equals x minus z1 to the k1. So for each point like this, where the coordinates are all distinct, I get a curve, in fact a compact Riemann surface, whose affine part has this equation. For this, to say that it's smooth, I have to assume something. So these numbers have no common factor. You know, if all these have common factors, it's a kind of degenerate square. So I have this family x over s. And one would like to understand what the monodromy group is. But you see, each of these curves has an automorphism by z mod d. If I multiply y by y times omega, where omega is the dth root of unity, the equation doesn't change. And the monodromy is doing something to the roots. It's sort of moving them around. So it has nothing to do with this. So this action commutes with the action on the monodromy group. By the way, the genus of these curves, of course, is fixed. I'll just give you the formula. I worked it out some time ago. Don't ask me to prove it because I don't remember. So the genus of this curve is given by n times d So again, the monodromy representation goes into the symplectic group, but it doesn't merely go into the symplectic group, it goes to a subgroup which commute with this action by Z mod D. So let's fix a generator here, generator. So I write like this, which means this is the subgroup which are fixed under the adjoint action of T, so which commute with T. I will say presently what this group is, it's in general a unitary group. This is not a symplectic group, it is usually of unitary type. And so what one is asking is, so I'll come to this in a minute. So it's a kind of unitary group. You see, because this T was multiplying by a fixed primitive dth root of unity, T to the D is equal to 1. So it goes. Yeah, okay. So pi 1s goes into a unitary group, but it doesn't, it goes into the these rational points of the unitary group. Because, I'm just saying that it commutes with T. So H is a form about which I will say what it is in a minute. I mean, it's the obvious form. So what we do is we have this symplectic form on the real vector space. On H1 of these curves, this has a symplectic form, the intersection form. So if omega 1 and omega 2 are here, I'll just take omega 1 wedge omega 2. But because I have the symplectic form on the complex vector space, this C is the same as this curve. This is the curve C. On the complex vector space, there is a Hermitian form. If omega 1 and omega 2 are here, I could take omega 1 wedge omega 2 bar. So that's the nothing has been done because it's the obvious thing. One just wedges it to the complex conjugation, except that the eigenspaces for this T live here. Right? The eigenvalues, in general are not real or complex. So each eigenspace of T is preserved by the monodromy group. But you see, I have just the cyclic group, so there is a cyclic generator, and so I am just looking at eigenspaces for this one linear operator. So they are all parameterized by